And continue the applause to introduce the final speakers of this session before we go to lunch. To my left, your right, I have David Bouchard, and he will be presenting with Steve Daniels, who's standing behind me, from Ryerson University, a paper on called Tiles That Talk, Tangible Templates for Networked Objects. The floor is yours.
Thank you. Okay, good morning, everyone. It's a pleasure to be here. So our talk today, Tiles That Talk, Tangible Templates for Network Objects. We're going to be introducing a toolkit we developed for one of our classroom. So I'm going to start by giving you a little bit of context, where we come from with this. So Steve and I teach in a program called New Media, and it's a fine art program for undergraduate students where we play with art and technology. One of our courses deals with networked art, and this would be one of many possible examples. This is a piece called Telephonic Arm Wrestling by Norm White and Doug Back from 1986. And if you're not familiar with this work, I'm sure it does exactly what you think it does. It allows two people to arm wrestle at a distance. So we introduce students to this idea of making artworks that involves connections between two or more devices, and give them the technological tools so that they can make work of their own in that space. Now, as we've been teaching this course, we obviously run into some challenges. So let me define the problem space here a little bit. So our art students have much stronger conceptual skills than they have programming skills. And we do have some introduction to programming in our curriculum, and a little bit of physical computing as well, but it's very much at the introductory level. Now, when you start programming for networks, literally it demands a lot of components falling into place in order for the communication to start happening. And that can get finicky if you don't get all the right components talking to each other and set up right. Then you spend a lot of time troubleshooting, a lot of time doing your actual project. So we were trying to think of a way that we could help enhance their experience in the classroom, kind of provide them a teaching aid, essentially. And this idea that lots of things need to fall into place led us to draw some inspiration from tangible programming toolkits, which is where we kind of started from. These are three well-known examples to this community, and the one that we borrow most heavily from would be the one on the left. This project called Turn. The one in the middle is flow blocks, and then algo blocks on the right, but there's actually countless other examples as well. All of these toolkits are looking at making use of tangible blocks to represent programming languages. They're aimed mostly at children, whereas our audience is quite a bit older. We're working with sort of young, early students in their early 20s. But nonetheless, we drew a lot of inspiration from these projects. So what I'll do now is we brought a video with us. I'm going to use it to hold on there. I'm going to use it to introduce our project. I'm going to pause at different times and kind of use the video as slides. So this is kind of what we came up with as our toolkit for our network class. I'm just going to pause it here for a second. So hopefully you get a feel for what we're going for here. So rather than creating a toolkit where we can teach students how to program, here we're looking more at higher level. Oh, thank you. Higher level abstractions. So this is more about sort of system diagram and allowing students to prototype the general network topologies that they're going to be working with. So this would be a simple example where you have a processing sketch talking to an Arduino board over serial and using an open sound control protocol to mediate that communication. So what just happened here is, so we've seen on our tiles, we've put in optical tags. These are called top codes. They've been developed by Michael Horn. And so we then take a picture of the system, and what students get back is a series of code templates that just provide the basic scaffolding for that particular network chain. So using the kit that students are provided, they can start to play around with different possibilities, different network pathways. So in this example, we've added 2 tiles to the chain, which represent Zigbee technology. And on the one side, there's a piece that represents hardware for their Arduino, which would be a Zigbee shield. On the other side, we have a little Zigbee Explorer board that needs to be connected to the computer. So we've been trying to do a few things with these tiles. One is to kind of maintain the symmetry of the hardware so that it literally represents the physical and software chains that need to happen in order to create these networks. And we've also paid close attention to developing the connectors in such a way that you can only connect together software and technologies that can actually talk to each other. So as long as you start with endpoints, you'll always end up with a valid network. Color-coded them as well to help students see the different stages. So yellow are protocols, and then the red tiles here represent hardware. It actually matches the color of the hardware that they get on the shelf. All right, I'm going to just stop it here and move on to the next slide here. I'm going to pass on the mic to Steve. So we will take a few minutes to talk about outcomes.
So we just want to describe a little bit how this has shifted our pedagogical strategies, because since writing the paper in the summer and submitting to the conference, we've had the opportunity to work one more time with these tiles in the classroom. And historically, if we were to teach students about network objects, we would probably set up a context like, let's make this physical object talk to this data space inside a laptop. And we would hand out a sample file and say, here's sort of some beginning code that gets you started and it works. And it's kind of a weird situation, because you say, here's the problem, here's the answer, let's pick at the answer and decide if it's good. And now what we can do is say, here's the problem, here's a collection of pathways, find your own answer. And we can set the students out to seeking for a solution right away. And they can be working with their hands in a tangible space, pulling apart the different pieces of a network on their desktops before they actually get into the act of trying to build a system inside their classroom. So it shifts the dialogue that we have with our students in a really important way. It also empowers students to seek and construct their own solutions. We find students tend to explore more than one solution now to a problem, because it's very quick for them and they have a lot of confidence in building a new kind of pathway. And we've also discovered very recently that we can invert the whole system. We can use it as an analysis tool. So when we hold up a piece like that David introduced at the beginning, like Norman White and Doug Back's telephonic arm wrestling, we can say, think about this as a networked experience and build the tiles that reflect what the experience is doing and how the network impacts the experience that's already been constructed. So while we developed initially to say, let's build cool things, we've also realized that we can use them the other way and analyze cool things and analyze those networks and bring that information back into the classroom. And I think most importantly as instructors, one of the things it does is it's liberated huge amounts of time for us. When we first taught this course, we would kind of spend, we have a 12-week term, we'd spend 4 weeks of the term debugging sort of parsers and how do you get the information actually to land in the right computer at the right time. And now with these tiles, we can sit down in a classroom with 30 students and we can prototype maybe 15 networked objects inside one single 3-hour block. And now we can take those 4 weeks that we just recovered from parser lessons and start talking about, is this conversation meaningful? When these two technologies talk to each other, is this actually experiential, or was this just a huge programming problem-solving space? And we've shifted now the dialogue in our classroom from one about how do you get two computers to talk to each other to how do people speak to each other through networked experience. And with that, we'd like to just thank our funders, our supporters, the organizers of this conference for 3 really challenging days, everyone who chatted with us last night at the demos, and perhaps open the floor to questions.
There's time for 2-3 questions.
Hi, Daniel Ashbrook from the Rochester Institute of Technology. I'm curious if it's clear to your students what is a software configuration and what is a hardware configuration. In the very beginning of the video, you showed a serial port connected to an Arduino connected to some output, and then you showed essentially the same thing but with OSC in the middle, which does not change the hardware configuration. It's just something that's happening in software. And so there's a little conflation there that I see between what's physical and what's not.
Yeah, it's a good question. For example, this is something we try to address, the fact that we have 3 different OSC tiles, and you can interchange them with different hardware. So this is meant to represent that this part is not hardware dependent. It will sort of fit into lots of different contexts, for instance. The other thing that also comes, and I'm sure that if that addresses your question, we don't touch it on the video so much, but the other thing that comes along with the code templates is, let's say in the case of XP radios, we also generate sort of PDF instructions that are customized to address more of the hardware configuration that we just can't do in code. So things like doing the settings and the addresses on the radios. So that's also included in their zip files. So they get their customized kind of instructions on how to move forward.
Yeah, that's nice. I had one other question, which is more of a practical question. I'm just wondering if you ever run out of configuration space, if you end up with tiles trying to sit on top of each other.
The configuration space is actually quite limited in the end when you start to look at it. It's very finite. There's only so many ways you can arrange these tiles, but we found that it's enough for what we want our students to be playing with, and it gives them enough options so they can connect Arduinos to Arduinos, computers to computers, or any kind of mix of the two. We also are working recently to add an Android tile to the mix so they can also bring mobile devices. But we've kept the space of connections limited in a way just to help prevent what you described. So we're not trying to make it the toolkit so that you can cover everything. If a student could deal with that, they probably don't need our toolkit. They'll be comfortable enough to create these insane networks. Right?
Your findings from using it this semester are really encouraging, and you're saying how it's changed the dialogue and they're coming up with more ideas. I also wondered whether, because it's an external representation they're using, is it encouraging them to talk more, to collaborate with others in the class than just doing it by themselves? Did you find that at all?
I would say yes, based on observation. I mean, we haven't formally studied that to see if that's the case, and we don't really have anything to compare to. But definitely, one thing that we've noticed, and I think this is a nice benefit of doing this as a tangible interface. I mean, you could easily imagine this being a web app with those blocks that you can use to diagram. One thing we run up against all the time in the classroom, and I'm sure all of you teach undergraduates or even graduates, is digital distractions, right? And if you're doing something in the computer, you're competing with Facebook at the same time usually, and all kinds of multitasking. What's been nice with the tiles is that it kind of allows us to break the classroom dynamic a bit, and it gives us an excuse to do an activity that's not computer-based. And students are now focused on that task and that task only. And I feel that that's been very beneficial. And then what they end up talking about is what's in front of them and not necessarily all those distractions. So.
Final question on the right side.
Hi, Dimitris Manicolau from Harvard GSD. Thanks for your presentation. I was wondering, why did you choose to use physical blocks instead of visual programming language, like, for example, Scratch?
Right. I mean, that's actually what I was just kind of answering her question in an indirect way. We felt, for a number of reasons, and the distraction angle, I think, is a nice one, and we wanted to create an activity that would break from the routine of being on the computer all the time for students in the classroom. So they can collaborate with each other more easily to solve problems. They each get a kit, and if they want to create a more elaborate network, they have to start sharing pieces. And because we just give them a pile of tiles and we start with the endpoints and we tell them figure out how to make the connections, we feel that it's a lot quicker to be able to manipulate the pieces physically rather than virtually, and you get to feel which ones don't connect with one another, that are incompatible, much more viscerally than you would if you're just dragging those objects on screen for that particular application.
Just a follow-up. I was wondering if you're planning in the future to make any user study with students where you would compare both a physical implementation like this one together with a visual.
Yeah.
That would be interesting.
Yep, it's something to think about for sure. We've got a lot of feedback, especially in the demo, about doing something like that. And I would say, yeah, why not? Maybe that would be.
I'm saying that because I think it would be interesting to see whether indeed students will find the physical blocks more useful rather than visual representations.
Yeah, absolutely. It's a great idea. Thank you.
We have time for a last question over there.
Yeah.
Okay, the last question.
Last question. At Unity in Twente University, I used to teach physical computing a lot myself, so I really love this work and really love the tangibility of it. To what extent do you use this tool for students who are already experienced with the tool set? Because explaining about OSC, of course, they have to know what the tile represents before they really can appreciate what is going to represent in the whole system. So what kind of pre-knowledge do students bring before you let them play around with your tiles?
The question's on pre-knowledge. Maybe you want to tackle that one?
I guess there's a couple of ways to look at that. Students, when they get to this networking course, have already taken an introductory course on physical computing, and they've already taken an introduction to programming. So they have a bit of a sense of things, but it's still kind of early on in their exploration of the technological applications. I think that the tiles, what's really nice is even experienced students who feel very confident in these spaces, it allows us to have these higher level conversations and break down and model what the network looks like. Networks are really tricky to teach because they're invisible and we can see their effects, but it's really hard to kind of describe how the connection space works within the technology and how that's going to impact an experience. So we can lay those tiles out on the floor, and even if someone's really comfortable in the space, the technological spaces of playing with different physical elements, the conversation, we can kind of be working with the tiles as a roadmap through a project. And one of the other things we've noticed is you can start to decouple the trains and break up groups, and groups can take kind of half of a tile chain and the other group can take the other half, and they can start to work simultaneously on the different problem space, and then literally we bring the groups back together and reconnect those tiles, and now we have a completed sort of experiment or exploration. And so they're a little bit equalizing, probably more so for the weak students, but they certainly still work topologically for the students who are much more confident in the technological spaces.
Great. Let's thank David and Steve and all the other presenters in the session.